The second speaker in this series of public lectures this afternoon is Professor Andy Strominger. So, Andy Strominger is the Guil York Professor of Physics and the Director of the Center for Fundamental Laws of Nature at Harvard University. And he did his PhD work with Roman Jakiv at MIT. I can say a lot about him because I have a very deep admiration for his science. But let me be very brief because there isn't much time. So he has made deep and profound contributions to fundamental physics, which are historic landmarks in our quest to discover the fundamental laws of nature. And I think I'll mention of the many discoveries he has made, basically two for this introduction. So he's the co-discoverer of the famous Calabi-Yau compactification of string theory, which is a very early attempt in the 1980s to unify elementary particle physics and quantum gravity in 4 dimensions in some realistic model. With Kamran Wafa, he established that the Hawking-Bekenstein entropy of black holes can be derived from Boltzmann's counting formula, which is very well known in statistical mechanics and thermodynamics. In my view, this is one of the most important results in string theory because it established without doubt that quantum gravity has new degrees of freedom. For his work, Andy has been awarded many prizes, but let me mention the Dirac Medal, the Oscar Klein Medal, and the Breakthrough Prize in Physics. He is a member of the US National Academy of Sciences. Now, Andy has been associated with the string theory effort in India for a very long time. And in fact, he created a fund from a donor at Harvard to support string theorists from Tata Institute and Harishchandra Research Institute to participate in international string meetings and other similar visits. And I do remember his statement that from India, we have the highest contribution per dollar in the world in string theory. With these few words, it's a great pleasure to invite Andy to deliver his talk.
Thank you, Spenta. It's a pleasure to be here in India and in Bangalore, which I have come many times, as it is one of the great centers of theoretical physics in the world. So what I'm going to talk about today is the edge of the universe, black holes, horizons, and strings. It's roughly the same topic that you just heard about from Nadi Seiberg, except that since we have no idea what this edge is, the talk will be unrecognizable as being on the same topic. So the quest to understand the laws of nature at their most basic level has been going on for hundreds or thousands of years. And what I'm going to talk about today is the edge, the things that the edge of our knowledge, the things that we don't understand but think we might soon be able to understand. And those are the most interesting things in science. Not some of the most difficult questions, like why are there 4 dimensions, or we don't even know how to think about their resolutions. And the most interesting ones are the ones that lie right at the edge, but we don't have a map that will tell us how to go beyond that edge. And interestingly, the edge of our knowledge, in some sense, or much of it, coincides with the edge of our visible universe. our universe is bounded by regions that surround, for example, a black hole or a cosmological horizon in which we physically can't see. But even though physically we can't see in there, our minds can go past that edge and try to understand what is in there. Now, it's a really fantastic thing how much we do understand about the world if you stop to think about it for a minute. We can launch a rocket from the Earth, which undergoes some crazy complicated trajectory, lands on Mars, and we can predict when it will land there within the second. We understand in incredible microscopic detail how the delicious spinach saag and chicken masala that I had for lunch is being metabolized, turned into sugar, and enabling me to speak. So we know just an incredible amount about the world around us, yet at the same time, there are very basic questions which I have been asked by a 3 or 4-year-old about what's going on around us, like how did the universe begin? And other questions which Nadi listed for us. So we've been pushing the edge forward for thousands of years, and we want to continue to do so. And what is the best way to do that? Well, the best way is to find what Nadi referred to in his beautiful talk as the clouds. And one of the clouds that he didn't mention was Einstein's. There are many of these clouds. And of course, it's the trick of a physicist. It's not a science, it's an art, to know which clouds, to guess which clouds are going to evaporate and be uninteresting, or which clouds are the harbingers of thunderstorms. And so Einstein came across the following cloud. He thought about what would happen if he held a mirror in front of his face and ran faster than the speed of light. At that time, in 1905, Maxwell had already understood what the speed of light is, and he realized that if he used what Maxwell had told him, that that would tell him that the image would disappear from the mirror, whereas if he used Newton-Galileo's laws of motion, the image would stay. And this bothered Einstein quite a bit. And Einstein, of course, was a very talented individual, but he could not actually run faster than the speed of light to do the experiment. But his mind could. And he thought about it very deeply. And he ultimately came up with the conclusion, just from this little cloud, he picked the right cloud, that nothing could go faster than the speed of light. This is the foundation of special relativity, and it affects everything that happens. All technology is based on this. It led to this discovery of atomic power, and it has completely changed not only the physical world around us, but the way that we think about the very nature of space and time itself, just by picking the right cloud. Now, there have been many such clouds in the history of physics. And in fact, every great revolution in the way that we understand the universe about us has had one of these clouds behind it. For example, if you put together the laws of thermodynamics, which tell you how fast, if you put some gas under a pot of water, how long does it take it to boil? That's a law of thermodynamics which was understood in the 1800s, and you put it together with Maxwell's theory of electromagnetism, you get an infinity that's called the ultraviolet catastrophe. Fixing up that cloud, which was indeed a thundercloud, led to quantum mechanics. Then we had that special relativity, Einstein's observation that nothing could go faster than the speed of light, was inconsistent with Newton's law of gravity. Because in Newton's law of gravity, the strength of the gravitational field travels instantaneously. If the sun moves an inch, according to Newton, the gravitational field, its gravitational pull, changes everywhere instantaneously throughout the universe, much faster than the speed of light. And that contradicted Einstein's theory. And to fix that, he had to come up with more completely wild ideas, namely general relativity, the idea that space and time is curved. Now, all this sequence of developments in physics culminated in the 20th century with something called quantum field theory, which was what Nadi was talking about during about half of his talk, and general relativity, Einstein's theory of gravity. And wouldn't you know it, they are incompatible, which is it's the best gift that a physicist could have, because we have these two incredibly well-tested, beautiful, coherent theories, yet they are inconsistent. And there have been proposals, string theory being the leading one, about how the inconsistency might be resolved, but we don't yet know how that will work. So I want to tell you more about what this inconsistency is. It has several aspects. So let me give you a crash course, one slide each, on quantum mechanics and general relativity. So in general relativity, matter, such as the sun, causes space to be curved. And so the space around the sun is curved, and it's much like if you put a bowling ball in the middle of a trampoline. If you put a bowling ball in the middle of a trampoline, and an ant starts to walk on it, and the ant is instructed to walk in a straight line, put one foot in front of another, it will actually walk in a curve. So something moving in a straight line in a space which is curved looks like something which is moving in a straight line. So all objects, the Earth, the sun, and the moon, are actually moving in straight lines. It may not look like it, but this little blinker just was moving in a straight line. It's just that you don't know the details of how space is curved, that is actually a straight line. And so the force of gravity is actually an illusion brought about by our unawareness of the fact that space and time are curved. Now, what about quantum mechanics, the other great discovery of the 20th century? So quantum mechanics says that things are not quite as certain as they at first appear. So you cannot know with certainty the position and the velocity of any object. So it may look as if I'm standing perfectly still at fixed position here on the stage, but in fact, according to the uncertainty principle, I must be wiggling around a little bit. But the wiggling is fantastically tiny, and it's so tiny that it was thousands and thousands of years and powerful microscopes that were needed in order to observe it, but it is certainly there. So that's quantum mechanics. Now, what happens when you try to put together quantum mechanics and gravity? Well, a very elementary argument says that the thing which becomes uncertain when you apply quantum mechanics and gravity is space-time itself. And for thousands of years, when people wrote equations for physics, they start with space-time as a fixed, immutable background, the arena on which everything else is played out. Now we no longer have that. It's as if the blackboard on which we were writing our equations demanded to be part of the equations itself and started moving around. So we're just kind of lost. We don't know what to do. And so we need a very new way to think about these things. And I think there is general agreement that when we understand how quantum mechanics and general relativity fit together, there will be, along with that, a new view of the universe around us that is more revolutionary even than quantum mechanics and general relativity itself. And I will quote Nadia here again, since he's gone. I have no idea what that sentence meant, but I'm sure it's right. OK, so what is this inconsistency? Well, there's something that was developed in the 20th century. It's kind of like a food processor. You take classical laws of physics, the classical laws of physics that were discovered in the 19th and 20th century, and you put them in together with quantum mechanics, and you put them through this food processor. There are many textbooks on the details of what's inside here, and out comes a theory which consistently harmonizes harmonious flavors, consistently puts together quantum mechanics with any other force. And in the 20th century, much of the history of 20th century physics was understanding the food processor called quantum field theory. There were 43 Nobel Prizes given for the details of what's inside there. Spectacularly successful, the most accurately measured. The output of this food processor has been measured to 14 or 15 decimal places, the most successful and accurate theory in the history of human thought. But it doesn't work with gravity. You get garbage out the other side. So that's our problem. This is the 20th century. Fixing up this food processor is the 21st century. Now, we in fact have discovered an attachment. We don't know if it's the one that nature uses, but we've discovered an attachment called string theory, which does enable one to put them together, but we don't know if it's the attachment that nature actually ordered. Now, because of this paradox, the courses that we teach at Harvard in physics are not consistent. If you take physics 143 and you try to use that to calculate some things, or if you take physics 210, calculate some things, you will get different answers. I'm not including here string theory, which is a higher number, 287. But we don't know if that will give you just one answer, but we don't know if it's the right one. Now, there's a second aspect to this puzzle, which is related to black holes and to some important work of Stephen Hawking. And so now I'm going to change the subject and talk about black holes. So what is a black hole? Well, on Earth, if you want to send a rocket into outer space, ignoring the effects of the atmosphere, if you send it up from the surface of the Earth at 11 kilometers per second, it will escape the Earth's gravitational field, and it will go on forever. It's easier to get off the moon. There you only need to get up to 2 kilometers per second. But if you get too much matter in one place, the escape velocity climbs up to the speed of light, and then nothing can get out because nothing can travel faster than the speed of light. In fact, not even light can get out. So these things are black, and that's why we call them black holes. Now, black holes have an amazing history. We're about to hit the 100th anniversary of the discovery of the black hole by Schwarzschild. Einstein wrote down his famous field equations in 1915. It's said that he thought nobody could find an exact solution of them. But Schwarzschild solved them a few months later, and the so-called Schwarzschild solution, which we now understand is a black hole. And the form of this solution was so strange and so disturbing that even though nobody could argue that it solved the Einstein equation, nobody believed them. And in fact, Einstein himself, in 1939, 25 years after Schwarzschild's discovery, wrote in a paper that there were no such things as black holes. And he gives an argument here for which I would flunk anybody who wrote that on my general relativity course. So I think we now understand, it took a long time to understand what a black hole is, probably 50 years. And even Einstein himself did not understand what they were. But now we do understand much of their classical properties, and we see them all the time up in the sky. And in fact, we think that there's a huge one that's 1 million miles across, around which all of us, in the center of our galaxy, Sagittarius A star, around which all of us are now orbiting. So we have to live with them, and we have to understand them. Now, what is a black hole? Well, it depends on how you try to describe it. According to the Schwarzschild-Einstein description, a black hole is, in fact, nothing. The universe ends at the edge of the black hole, which we call the horizon. And when I say nothing, I really mean nothing. I don't mean like in the room here, this isn't even empty space, there's air. But even if we got off the Earth where there's no air, you would have empty space. In the middle of a black hole, there isn't even empty space. There's nothing. This disturbs people. And moreover, things which go into the black hole cease to exist and dissolve into nothingness. Even more disturbing. Now, that's what we believed up until the early 70s, when Stephen Hawking came along and he said, wait, what about quantum mechanics? What happens if I try to describe what happens in the quantum world when there's a black hole around? And he discovered something very strange, which is that when you have a black hole in the quantum world, radiation does come out. In fact, all possible forms of radiation come out very, very slowly. And there is a little bit of light that comes out of a black hole, and they will slowly evaporate and disappear. And he gave a formula which takes the form of a thermodynamic law, which tells you how hot a black hole is as a function of Newton's constant of gravity and its mass. Now, thermodynamic laws, the laws of thermodynamics, I talked about them a moment ago. They tell you how long it takes to boil a pot of water, have been one of the central topics of study in physics for the last several centuries. And Boltzmann, I won't try to describe this in detail, but in really one of the most beautiful developments in the history of thought, Boltzmann showed that the laws of thermodynamics follow from statistical reasoning applied to molecules. In other words, if you know that water is made up of H2O, which, by the way, they didn't when Boltzmann gave his argument, but if you assume that water is made up of molecules, you can use statistical reasoning of where the molecules want to be to deduce or derive the statistical properties. And an important ingredient of that is how many different configurations of molecules there are. That's called the entropy. We can also think of the entropy as the amount of information, the amount of configuration. It's like the number of gigabytes in your computer. The number of gigabytes in your computer is how much information, how many configurations there are of the chips in your computer and how much information it can store. So Hawking working back from his thermodynamic formula for the temperature, he was able to infer how much information, how many gigabytes there are in a black hole. And he gave what I view as a central and very fundamental and very mysterious formula in modern physics, relating the number of gigabytes, the entropy in a black hole, to the area of the surface that surrounds it. And this is a formula which brings in everybody. It brings in information theory, it brings in gravity, brings in math, there's a 4 there, brings in Newton's constant. The 4 is important because it means that there's something precise to calculate. There's no hand waving here. Brings in quantum mechanics. Everything we want to understand is all together in this beautiful, mysterious formula. And by the way, it's a very big number. If you took all the information in all the Google data banks, it would fit inside a black hole, which was a trillionth of a millimeter. There's something called Moore's law, which says that the amount of information you could put on a computer chip of a fixed size doubles in every some number of years. I think it's 3. And it keeps growing exponentially. And eventually, though, Moore's law must fail due to black holes, because we believe that the black holes are the best information storage devices that can exist in nature. But it will be a long time. OK, now, if you've been paying attention, I've told you 2 things which are in complete contradiction. I've told you that black holes, there's nothing inside a black hole, not even empty space. And at the same time, I've told you that they're incredibly complex objects which can store vast amounts of information, far more than anything that we've envisioned. And this is certainly looking to me like a cloud which is going to be a thundercloud and is going to a contradiction from which we can really learn something. I think this is a real gift to physicists that we have this wonderful puzzle that we can sink our teeth into. Well, this puzzle was apparent when Hawking wrote his seminal paper in 1974, and we didn't know what to do with it. And like many advances in science, a piece of the answer or some insight into it came in a strange way. And it came through string theory, which the beginnings of it came through string theory, which we didn't really begin to investigate in order to understand this problem. It was investigated for other purposes. And let me just say 2 words about string theory. The basic idea of string theory is that if you look at particles under an extraordinarily powerful microscope, you will learn that they are not point-like after all, but they are little loops of string. And these little loops of string can vibrate in different ways. And just as a guitar string, if you pluck it in one way, it will make a C. You put your finger on the 12th fret and you pluck it again, it will make an octave higher. Just as a guitar string can sound different depending on how it's vibrating, strings can look different depending on how they're vibrating. And quite miraculously, we have learned that they are capable of masquerading as every single one of the elementary particles, the electron, the quarks, the photon, et cetera, that we observe around us. They're capable of doing that. Whether that is the real nature of elementary particles or not, we probably won't know for some time. Now, that's the original description of string theory. That was some 40 years ago now. And since that time, the field has grown in many different directions and combined many different ideas, some of them which do not rely much on strings at all. Now, as Nadi said, it will be very hard to get direct experimental evidence for string theory. But in the meantime, we can use string theory to try to address some other problems. And so one of the advantages, physicists are not very good at abstract reasoning. We like to have equations we can get our hands on. And string theory is supposed to incorporate quantum mechanics and gravity. And if it does so, it must somehow resolve this black hole information puzzle. If it doesn't do that, it's wrong. And so we realized that, and so we had some very concrete set of equations, and we pushed forward to see how string theory might resolve this puzzle. And even if string theory in itself is not the theory of nature, the way in which a black hole, we might still learn how it is possible for a black hole to simultaneously be a maximally simple object and a maximally complex object. So Kumran and I, who is the next speaker, looked at this problem in the context of string theory in a very special context, and we discovered that, in fact, string theory could explain how there were so many states inside a hole of nothing. And it did so by surrounding the black hole with a holographic information plate. Much like a hologram, you have a two-dimensional plate which projects a three-dimensional image. And that is how the black hole did it. And we showed that this reproduced the prediction of Bekenstein and Hawking, including the important 4. And it gave a procedure by which maximally simple and maximally complex descriptions of black holes are complementary but perfectly compatible descriptions. And I'm just more precisely, there are some very precise equations and beautiful mathematical equations behind this, which I won't try to explain. But let me put it more simply. Suppose we have a theater in which there are 66 seats, and one person says, the situation here is very complicated, spends a long time counting, and says there's 65 people in here, and the other person says the situation is very simple, there's just one person, and then they argue. They say one says it's 1, the other says it's 65, and they're just looking at it from different points of view, and they realize that when they learn to add, and 66, the number of seats is 65 plus 1, and these are just two different descriptions of the same thing. So the description of a black hole as a hole of nothing and as a maximally complex object are completely equivalent mathematically. They are just starting from complementary points of view. But the mathematics that was needed to show this was not simple addition. The mathematics that was needed to show this needed to be discovered in order to solve this problem. But now we understand a lot about that mathematics, and we hope to apply it not to the black holes that exist only in string theory, but to the black holes which we see up in the sky. And once we've learned the trick that string theory has used to reconcile complexity with simplicity, we shouldn't need the details of the theory to explain the black hole puzzle. And after all, Sagittarius A star in the middle of our galaxy is 1 million miles across. We shouldn't have to know the nature of tiny little objects that are trillionth of a millimeter in order to explain this huge object. So we want to understand the black holes that we see in the sky. And it turns out that there are different kinds of black holes that we see in the sky. And some of the black holes are simpler than others. And it turns out that black holes can spin, but there's a maximal amount that they can spin. And that maximal amount is when the horizon of the black hole is moving at the speed of light. And black holes exert a lot of force on everything that's around them. And if a black hole is spinning at the speed of light, everything near it must also spin around at the speed of light. And it's very hard to go at the speed of light. And if you go at the speed of light, there are very few ways that you can move. And so things which are moving around at the speed of light are actually very simple. And we were able to use some tools to analyze that special case that were not generally available. And it turns out that the black hole which has been most studied astronomically, GRS 1915 plus 105, is spinning at the speed of light. And there are several others, including the first one ever seen, Cygnus X1. These are very rapidly rotating objects. And here's a picture of how we see a black hole. Of course, you can't see them because they don't emit very much light. But here's a picture, an artist's rendition of GRS 1915. There's a companion star. Matter is pulled off it. It spirals in a disk. There are jets which go up and down out of the black hole. And the black hole, of course, we can't see. We can see what it does to the matter around it. And it is sitting in the very center of this object. And that is the mysterious object that we wish to understand. We wish to understand what the information is inside that black hole. And we don't want to understand this whole picture. We just want to understand what happens very near the, I guess the audio isn't working, but this is a NASA, oh, there we go. A NASA video of zooming in to the center of this disk of matter that surrounds the black hole. And the black hole is sitting right there in the middle. And that's what we wish to understand. And understand whether that is a hole of nothingness or whether it holds a huge number of gigabytes. Now, in this special situation of these rapidly rotating black holes, it turns out that there's a symmetry that appears right where the holographic plate surrounding the black hole lives. And this symmetry was the key ingredient. In the work that I did with Vafa, we started with string theory, then we derived this symmetry, and then we used this symmetry to understand how the black hole stored the information. And for these rapidly rotating black holes, we can get to that symmetry without presuming string theory. And so we would like to understand if it is the case that this symmetry exists also for these rapidly rotating black holes, as seems to be implied just by the Einstein equation. So that the situation that we understood in string theory actually is manifest in the observable world. So we can ask, what are the observational signals of this symmetry? And in fact, we have just reached, astronomers have just reached a threshold where we are about to enter an era of precision black hole spectroscopy. In other words, we have learned very indirectly about black holes by seeing stars and so on orbit them, but we haven't, up until the next few years, we haven't really been able to focus in and see them in enough detail to see if this conformal symmetry is actually there. And there is an experiment which is already funded and which will come online in a year or two called the Event Horizon Telescope, which is going to be able to image two black holes up in the sky and look at in detail at this little region right around the horizon. This is a picture. In order to do this, one has to synchronize a dozen or so radio telescopes scattered all around the globe. This is a picture of one in Chile. And they're going to be able to see two black holes. One of them is going to be the one at the center of our galaxy, Sagittarius A star. Unfortunately, that one does not have a big disk around it, so it's harder to get information about it. But there's also a black hole which is further away, but 10,000 times bigger than Sagittarius A star. It's at the center of a galaxy called M87. And it has dramatic jets coming out of its pole, which suggests that it may be one of these rapidly spinning black holes. And so now we are trying to understand when this telescope turns on, whether we will be able to see this conformal symmetry and learn whether these ideas that we stumbled into in string theory have some relevance in the observable sky. Now, I've talked about a lot of things. There have almost been only one or two equations in this public talk. And I think Nadi must have felt this after his talk, and Coleman will probably feel it also. It is a little bit as if you went to see, here I'm talking about the Grand Canyon, but if you go to the Taj Mahal, you go and see the Taj Mahal. I've seen the Taj Mahal. It's very beautiful. You see the Taj Mahal, and then somebody comes who says, tell me why the Taj Mahal is so beautiful. You don't have any photographs. You just have to explain in words why the Taj Mahal is beautiful. It's very hard to do. And explaining why the Taj Mahal is beautiful is like trying to explain what we're doing without using the equations. And the beauty of it is in the details, and I wish I could do more, but it's the best I can do in an hour. And to us, to the few physicists in the audience, this is what gets us really excited. So we're exploring the edge of the universe. We start out trying to solve one problem. We solve another problem. We don't know what we're doing. We start out thinking about strings. Then we're thinking about black holes. But it's a wonderful adventure. And we've been moving forward, understanding amazing new things for thousands of years. And I am at least confident that that will continue. Whether we will get to the end of the road, whether there is an end of the road, I don't know. So let me stop there. Thank you very much.
We'll take a few questions, Andy.
Yes, let me get some water here.
Sure.
Yes, yes.
So before we take the questions, let me present Andy with a memento from the ICTS.
Oh, thank you, thank you. Should I open it or? No, okay. Yes.
Okay, so can I have a few questions?
Hello. I am actually a physics teacher in a school, and I see that the children today are very, very interested in knowing all the new things that are happening in physics, and they ask a lot of questions. But one thing that I find it very difficult is, even other people also might feel, is that you have only two kinds of literature, either on the internet or on the any books. One is completely for dummies, another is for completely 100% mathematics, which nobody understands. So the people who know physics to some extent, people who have some understanding of, let us say, 12th standard physics, for them, if we want to explain what is string theory or what is quantum physics, what is quantum field theory, so there doesn't seem to be any good material or literature which can help a little better, because I don't want to make it look magical. I want to make it look something solved, a mystery solved, rather than creating one. So is there any such thing that you guys have done, or any? Because when I see you talking and the person before that, it's very interesting. You made it really possible to say
Yes.
these things to normal public. So have you done anything in this regard?
No, I haven't, and I feel for you in your question, and I've been faced with this. You left off the third largest category. There are two categories: the physics for dummies, the physics that are too hard to understand. Then there are also the books that are full of nonsense, which unfortunately may be the largest category. It is a hard thing. I have taught some physics for humanists, some courses, and I could recommend a few books. I could recommend Steve Weinberg's Dreams of a Final Theory, the first 3 minutes. I could recommend Brian Greene's The Elegant Universe. I could recommend Stephen Hawking's Brief History of Time. There are some good books there, but they are hard to find. If it weren't so much fun to work on this stuff, I would write one, but it's too much fun.
Thanks a lot.
Sorry.
It would be very nice if you can write something. Mainly, so I have actually gone through the books that you have mentioned. Most of them are still in pure English and with a little bit of mystery in it. But it's still, what I would like is something which is something like Newton's formula, kind of a simple mathematics. And above that, building a very simple version of some string theory or quantum field theory, where it is not, mystery, it is not wrong, but a first step towards this.
Let me recommend this, though. There's a great center for theoretical sciences here. We have the present and future director, and I'm sure that they can give you detailed recommendations, because there are some books out there but they are hard to find, and it's very, very hard for the person who's not a professional physicist to distinguish, particularly the books which are full of nonsense from the good ones. And even within those books, there are specific chapters. The good books, certain chapters you don't want to read. So find a physicist friend. There are many of them here in Bangalore, and get some recommendations.
Hi.
Yes, okay. Please ask your question.
Yeah, I'm trying to get a general sense of what a black hole is. But now, a black hole is supposed to bend space-time to a great extent.
Yes.
Now, on the internet, many representations show bending space-time in one direction. Going by common logic, it's supposed to bend space-time in all directions. So wouldn't that be like a huge ball of a black hole?
Yes, I mean, I think that at some point, again, we need more precise mathematics for this, but I drew this picture. I would ask the professional physicists in the audience to close their eyes for a minute and shut their ears, but this is not too misleading. That there's a place here where the
It's supposed to have a definite center.
the center is not really there. It's a hole, more of a hole in space.
And this other thing I've heard about, the Booth's void, which is supposed to have a diameter of 250 million light years. And
I'm sorry, the what?
the Booth's void. It's supposed to be a void
Yeah.
in space, which is about 250 million light years as a diameter. Now, there are observations apparently that it slows down light. And one of the explanations to that was that was because of quantum fluctuations, where dark energy fluctuates into matter, and then matter antimatter pairs, and then they annihilate and form energy. So that's why they slow down time. So what do you think about that?
I'm not really enough of an expert on that to say whether that theory is correct or not.
And so I've also read the Feynman series, so I guess I would suggest that to the person.
Yes.
I guess
The Feynman series, I myself learned physics from reading. Those are great lectures. Of course, they're 50 years old now, so the more modern, more than 50 years old now. Yeah.
Thank you.
Hi. I don't know string theory, so my question may seem nonsensical. String theory, I believe, is a more geometric approach to unifying quantum gravity. And does string theory somehow, quantize space or define a discrete metric somehow on space based on the uncertainty principle?
No.
Doesn't.
No.
And would string theory in any way be concerned in how the structure of space that way, is defined?
Well, I think that a direction in which many arrows are pointing is that, in a way, the history of physics is the history of learning that things which are obviously true are wrong. So we used to think that obviously the Earth was the center of the universe. And obviously there was a preferred, that turned out to everything revolved around it. We learned that was wrong. Obviously there was a preferred reference frame. We learned that was wrong. Obviously things could move as fast as they like. That turned out to be wrong. And one of the things that we are still clinging to, and we have not yet learned how to let go of, is that the notion of space and time are absolute. And the very way we describe all the laws of physics depend on space and time being absolute. But a direction in which things seem to be going is that space and time are emergent, that it's only an approximate notion, and it has no absolute reality in the way that we intuitively think that it ought to. And we have mathematical models in which we can see space and time emerging, and in a sense, the hologram that I was describing is a piece of that. You start out with a two-dimensional holographic plate, and you shine the light through it, and the third dimension emerges. And so that is something which is beginning to creep in, the idea that space is an emergent concept is creeping in from many different points of view, but we are very far from knowing if there is any reality to that.
Take one last question.
Good evening, sir. So my question is pretty simple. So what exactly is a black hole made of? I mean, is it just energy, or particles, or both?
We don't know what exactly a black hole is made of. That is the problem that we are trying to solve. In the string theory example, we were able to give, so string theory is a complete theory, which, at least a mathematically complete theory, which includes everything. It's an all-encompassing theory. And in that context, we were able to give a complete and detailed description of what black holes were made of. But for a general black hole up in the sky, we understand that it must have a lot of complexity from the very general arguments that Hawking gave. But what exactly it is made of is a question which is still on the other side of that edge of our knowledge that I talked about on the first transparency.
Sir, when a black hole emits Hawking radiation, why doesn't it happen that the matter particle of the couple falls into the event horizon and the antimatter escapes so that it gains mass?
So, yeah, that is a very confusing and puzzling point. But it turns out that you're alluding to that particles in, so here we will have a 20-second physics lecture. So the energy of something, you have a rest mass energy, and then you have something called potential energy, which is negative. So there's a component of energy which a particle can have when it's near a black hole, which becomes negative. So you pair create. The process of Hawking radiation can be understood as a quantum tunneling process in which two particles pop out of the vacuum, one with negative energy, which goes into the black hole. And since it has negative energy, it decreases its mass and makes it shrink. And then the positive energy escapes and goes out to infinity.
Okay, I think we are running a bit out of time, so let's thank Andy again for a brilliant talk.